A relation is nothing but a subset of a Cartesian product. Symbolically, we write R is a subset of A cross B. So whenever a condition is satisfied from one side, it has to be satisfied from the other end also. Then only we say that it is a symmetric relation. All the relations cannot have all the three properties satisfied. If all the three types of relations is satisfied, we call it as an equivalence relation. Hello everyone, a warm welcome to one and all. This is your Shruti ma'am, lecturer in Vidhyaashram, the Temple of Excellence, Mysuru. So we are at the first session from the second PUC Mathematics chapter, Relations and Function. So in this session, we are going to discuss about the types of relation. Previously, in your first PUC classes, you have learned Cartesian product, relations and function, whichever you found it in a very basic form. Now in this session and in this class of second PUC, the very first chapter deals with the extended form of relations and function, and here we are going to study the types of relations, function and the concepts related to it. Now let's see what is Cartesian product. So we have learned that whenever you have any two sets, the Cartesian product will be written in the form of ordered pair. Suppose I take set A is equal to 2, 5 and set B is equal to 3, 7. Then how we are going to write A cross B? A cross B is a set of unordered pairs in the form of 2, 3, 2, 7, 5, 3 and 5, 7. This is how we are going to write the Cartesian product of any two sets. Now what is relation? A relation is nothing but a subset of a Cartesian product. Symbolically we write R is a subset of A cross B. How we say that relation is a subset of Cartesian product? Previously, I have taken an example of set A and set B. So, this is how a Cartesian product is defined. Now, let me define a relation from set A to set B such that R is in the form of the ordered pairs A, B, where A is greater than B. Do you find any ordered pair which obeys this rule? A is greater than B. See, 2 cannot be greater than 3, 2 is not greater than 7, 5 is greater than 3. So, therefore, the only element in the relation is 5, 3. So, just inserting some condition, we are writing the relation from A to B. Clearly, you can see 5, 3 is in the element of the Cartesian product A cross B. Hence, we say that a relation is always a subset of a Cartesian product. When we say A is related to B, so if we write an element in the form of A, B, if we write A, B belongs to R, that means A is related to B. Hence, we write symbolically in the form of A, R, B. That implies A is related to B. Now, let us study the types of relation. What are the types of relation? The very first types of relation is the reflexive relation. What do you mean by reflexive relation? Suppose I take set A and define a relation from set A to A itself. Suppose I have any element which belongs to the set A, then the ordered pair in the form of A, A must be present in the set of relations. That is, a relation R on the set A is said to be reflexive. We say it as reflexive only when for all A belongs to A, A must belongs to R. Suppose I say 1 belongs to set A, then 1, 1 must be in the relation set. Suppose I say -3 belongs to A, then -3, -3 must be an element in the relation set. Then only we say that A is reflexive or R is reflexive. So for all the elements in A, they should obtain an ordered pair in the form of A comma A, which is present in the relation set. Now let us take few examples to study about the reflexive. Now let me take an example of parallel to relation. So I am taking an example parallel to. Suppose we say two lines are parallel. So L1, L2. Let A be the set of all parallel lines. Then how we define a relation? Parallel to, that is L1 is parallel to L2, L2 is parallel to L1. Similarly, we know that every line is parallel to itself because a line again drawn on the same line L1 is again parallel. Since every line is parallel to itself, every line is parallel to itself, that means what? L1, L1 belongs to R. If L1 is an element in A, then L1, L1 belongs to R. That is, similarly, we have L2 and L2, that is L2, L2 because L2 is also parallel to L2. So, how many lines will be in the set A? All the lines are parallel to itself. Therefore, hence it obeys the property of reflexive. Hence, we say the relation parallel to is a reflexive relation. Let me take one more example of divides to. Divides to. So, this is one of the relation. Suppose 2 is an element in A. 2 divides 2. That means what? 2 divides 2 belongs to R. If 2 divides 2 means how we will write the relation? 2, 2 belongs to R. Because the relation we have taken here is divides 2. Hence, whenever any element belongs to the set A, that should satisfy the property of 2, 2 belongs to R. That means 2 divides 2 is possible. Hence, we say this is a reflexive relation. Hence, divides 2 is also an reflexive relation. Now, let me take one more example. I'll take the relation X is taller than X. Is it possible? No. X is taller than X is not possible. That means suppose I have any element which belongs to A, there exists element X, X which belongs to set R. But here in this relation, it is not possible. Therefore, this is not an example for reflexive relation. Now, let me take one more example of the relation R is equal to 1, 1, 2, 2, 1, 2. So, this is the relation set defined. Just verify whether it is a reflexive relation or not. Now, here we have 1, 1 belongs to R as well as 2, 2 belongs to R. So, for the set containing only two elements 1 and 2, we have 1 belongs to A means 1, 1 is in R, 2 belongs to A means 2, 2 is also in R. Hence, we write R is a reflexive relation. R is reflexive relation. Now, let me take one more example. Set R is equal to 1, 1, 2, 2, 1, 2, 2, 1, 1, 3 and 3, 1. The set A is defined for the 1, 2, 3 elements. Clearly, we can see here set A contains 3 elements, that is 1, 2, 3. For each elements, you have for 1, 1, 1, for 2, 2, 2, but for 3, there is no 3, 3. So, what we can write here? We don't have any element in the form of 3, 3 in the set R. So, therefore, we write R is not reflexive. So, this is how we study the relation on reflexive. That is, whenever any element belongs to the set A, then there should exist an element in the form of A, A in the set R. Then only we say that R is reflexive. So, the next type of relation is symmetric relation. What does the symmetric relation says? A relation R on the set A is said to be symmetric. If you have any two elements, that is A comma B belongs to A. Then suppose you have A comma B belongs to R, then it should satisfy B comma A belongs to R. So I'll take an example of perpendicular. So perpendicular to. So let me consider two lines L1 and L2. So this is line L1 and this is line L2. So clearly we can say L1 comma L2 belongs to R. L1 comma L2 belongs to R means what? L1 is perpendicular to L2. So can I write L2 comma L1 also belongs to R? Yes, I can write, because if L1 is perpendicular to L2, then L2 is also perpendicular to L1. So whenever these conditions are possible, we say R is symmetric. So this is an example for symmetric relation. Now let me take an example. A is brother of B. A is brother of B. So that means we can write A comma B belongs to R. Can I write B comma A belongs to R? No, I cannot write, because I don't know whether A is brother of B means B may be sister also. B may be sister also. So since I cannot write B comma A belongs to R here, therefore this is not an example for symmetric relation. So whenever a condition is satisfied from one side, it has to be satisfied from the other end also. Then only we say that it is a symmetric relation. So here this is not an example for symmetric relation. Similarly, we can say X is taller than Y means obviously Y cannot be smaller than X, or X cannot be taller than Y. So X is taller than Y, that should also implies Y is taller than X, which is not possible. Therefore, that is not an example for symmetric relation. Let me take an example of one more relation set. So let me take R is equal to 1, 1, 2, 2, 1, 2, 2, 1. So clearly you see here 1, 2 belongs to R. Also we have 2, 1 belongs to R. So for all the elements 1, 2 here, we have 1, 2 also in R and 2, 1 also in R. Therefore, this is an example for symmetric relation. So whenever any two elements is in the set A, suppose A comma B is in the relation set, then it should imply B comma A also in the relation set. Then only we say it is an example for symmetric relation. The third relation is the transitive relation. So a relation R on the set A is said to be transitive if for the three elements A comma B comma C belongs to A. If A comma B belongs to R, B comma C belongs to R, then A comma C belongs to R. Suppose I take a set 1, 2, 3. So suppose I have 1, 2 belongs to R, then 2, 3 belongs to R. Then obviously it should implies 1, 3 also in R. So the AC should also be contained in the relation set R. Then only we say that it is a transitive relation. So I'll take an example of parallel to. I'll consider three lines here, L1, L2, L3. L1, L2, L3. Suppose I write L1, L2 belongs to R. What does this implies? This implies L1 is parallel to L2. Suppose I write L2, L3 belongs to R. What does this implies? This implies line L2 is parallel to line L3. So L1 is parallel to L2. L2 is parallel to L3. Obviously, I can write L1 is parallel to L3. So these two condition implies L1, L3 belongs to R, which implies L1 is parallel to L3. Hence, this is an example for transitive relation. So this is how we define the reflexive relation, symmetric relation, as well as the transitive relation. So Now we have an equivalence relation. What does this equivalence relation means? A relation R on the set A is said to be an equivalence relation if R is reflexive, symmetric and transitive. All the relations cannot have all the three properties satisfied. If all the three types of relations is satisfied, we call it as an equivalence relation. R may be reflexive but neither transitive nor symmetric. R may be symmetric or R may be only transitive sometimes. So, whenever the relation R satisfies reflexive property, symmetric property as well as the transitive property, when all the three cases holds, then we say it is an equivalence relation. Now let us take few problems related to the types of relation. So here we have a question. Check whether the relation R on the set A 1, 2, 3 given by 1, 1, 2, 2, 3, 3, 1, 2, 2, 3, 1, 3 is reflexive, symmetric and transitive. So for reflexive, the element should be in the form of A, A. And for symmetric, if A, B belongs to R, then we should get B, A should also belongs to R. And for transitive, if A, B, B, C are in R, then there must exist an element in the form of A, C belongs to R. Let us see if all the three conditions are satisfied. For the elements 1, 2 and 3, we have 1, 1, 2, 2, 3, 3 in R. Therefore, R is reflexive. Now, let's see. Suppose you have 1, 2 inside the R, but you doesn't find any element 2, 1 in R. So, here 1, 2 belongs to R, but 2, 1 does not belongs to R. Similarly, we can take 2, 3 in R, but 3, 2 does not belongs to R. 1, 3 is in R, but 3, 1 does not belongs to R. Hence, this is not symmetric. Not symmetric. Next, we have 1, 2 belongs to R. 2, 3 belongs to R. So, 1, 3 belongs to R. So, therefore, this is an example for transitive element. For the elements inside the relation set, it should satisfy the given condition. The only elements inside the set R is this. Hence, if 1, 2, 2, 3 belongs to R, then 1, 3 is also in R. Therefore, R is transitive. Let us take the second problem. Check whether relation R in the set 1, 2, 3, 4 given by 1, 2, 2, 2, 1, 1, 4, 4, 1, 3, 3, 3, 3, 2 is an equivalence relation. To verify the given relation is equivalence, it should satisfy reflexive, symmetric as well as transitive. Now we have 4 elements in the set. So 1, 2, 2, 2, 3, 3, 4, 4. Also 4 elements inside the R. Therefore, R is reflexive. But we have an element 1, 2 belongs to R, but we don't have an element 2, 1 inside the R. Therefore, it is not symmetric. Next, we have 1, 3 in R, 3, 2 in R. So, therefore, 1, 2 in R. We have an element which satisfies the transitive property. Hence, the given relation is a transitive. But it is not an equivalence relation. Why? Because it is reflexive, it is transitive but not symmetric. Whenever only all the three conditions are satisfied, we say it is an equivalence relation. Now, let's take the next question. Show that the relation R in the set 1, 2, 3 given by R is equal to 1, 2, 2, 1 is symmetric but neither reflexive nor transitive. Similarly, we can clearly observe the relation set for all 1, 2 belongs to R. We have 2, 1 belongs to R. So, therefore, R is symmetric. But we don't find any element in the form of A, which belongs to R. We have 1 inside the set, but we don't find 1, 1 inside R. We have 2 inside the set, but we don't find 2, 2 inside R. Similarly, we have 3 in the set, but we don't have 3, 3 in the R. So, therefore, this implies what? R is not reflexive. Similarly, we have 1, 2 belongs to R and 2, 1 belongs to R. but 1 comma 1 does not belongs to R. So therefore what we can write? R is not transitive. See here we have 1 comma 2 and 2 comma 1, but we don't find 1 comma 1 inside the R. Therefore we can write R is not transitive. So the next question here, show that the relation R in the set 1, 2, 3 given by 1 comma 2, 2 comma 1 is symmetric but neither reflexive nor transitive. The same property we use, we have 1 comma 2 and 2 comma 1. So whenever 1 comma 2 is inside the R, then 2 comma 1 should also be inside R. Hence it's a symmetric. But we cannot find 1 comma 1 belongs to R here. So it is not there inside the relation set. Therefore it is neither reflexive, and for transitive we have 1 comma 2, 2 comma 1. Again we don't find 1 comma 1 belongs to R. So therefore it is neither reflexive nor transitive. Next question we have, show that the relation R in the set A is 1, 2, 3 until 14 defined as R in the form of x comma y, 3x minus y is equal to 0, x comma y belongs to A is not an equivalence relation. To show that it is an equivalence, we have to show that it is reflexive, symmetric and transitive. Here we have to show that it is not an equivalence relation. So let us write the relation set. So here since 3x minus y means we can write y is equal to 3x. So just take the values of x here. So if you take x is equal to 1, then y is 3. X is equal to 2, y is 6. X is equal to 3, y is 9. X is equal to 4, y is 12. We cannot write 5 comma 15 because 15 does not belongs to set A. See, the condition is both x and y must be inside the set A. Hence, the last element 14, we cannot write this ordered pair. Now, clearly you can see here, A comma A does not belongs to R. For any element inside the set A, you don't find any element in the form of 1 comma 1, 2 comma 2, 3 comma 3. That is in the form of A comma A. So, this implies R is not reflexive. Now take any element. We have 1 comma 3 belongs to R, but 3 comma 1 does not belongs to R. So this implies R is not symmetric. Now see here we have again 1 comma 3 belongs to R and 3 comma 9 belongs to R. But what about 1 comma 9? You don't find 1 comma 9 belongs to R. So this implies what? R is not transitive. So R is not transitive. So it is not reflexive, neither symmetric, nor transitive. So therefore what we can conclude? R is not an equivalence relation. Next question. Show that the relation R in the set 1, 2, 3, 4, 5, 6 given by A comma B in the form of B is equal to A plus 1 is not an equivalence relation. So let us write the relation set here in the form of A comma B. Substitute A is equal to 1, 2, 3, 4, 5, 6. So when you take A here, it is 1 comma 2, 2 comma 3, 3 comma 4, 4 comma 5, 5 comma 6. Now clearly you can observe the relation set. You have the elements 1, 2, 3, 4, 5, 6 in the set. But you don't find 1, 1, 2, 2, 3, 3 any element inside the R. So what we can say here, A comma A does not belongs to R. That is, for all A belongs to the set A comma A does not belongs to R. So therefore R is not reflexive. Similarly, you can say you have 1 comma 2 belongs to R, but 2 comma 1 does not belongs to R. So therefore, R is not symmetric. Next we have 1 comma 2 belongs to R as well as 2 comma 3 belongs to R. But 1, 3 does not belongs to R. So this implies R is not transitive. So it is neither reflexive nor symmetric and nor transitive. So therefore I can conclude R is not an equivalence relation. So it is not necessary that you should prove all the three results to be an equivalence relation. If one is not possible, whether it is not symmetric nor reflexive or not transitive, it is not an equivalence relation. But whenever the question is asked for 3 marks, you have to prove that it is not reflexive, not symmetric as well as not transitive. Then you conclude it as an equivalence relation. Next one. Show that the relation R in the set Z of all integers defined as x, y, x minus y is an integer is an equivalence relation. We again get the solution in the form of an integer only. That means for all x, y belongs to R, x minus y is also an integer. That means obviously it will satisfy all the conditions of relations. So now let's see. So first case, we are going to show that R is reflexive. We know that 0 is an integer. 0 is an integer. How we will get 0? Only when you subtract the number with its opposite sign. That means x minus x is an integer. See, what is the condition given? If x minus y is an integer, then x comma y belongs to R. So therefore, x minus x is an integer. Then what does it say? X comma x belongs to R. So therefore, what I can conclude? R is reflexive. Now let's prove the second property, that is symmetric relation. So what does it say? If x comma y belongs to R, this implies x minus y is an integer. So now let me take minus of y minus x. This is also an integer. So this implies what? Y minus x is also an integer. So again from the relation set, if x minus y is an integer, then x comma y belongs to R. If y minus x is an integer, then what does it implies? Y comma x belongs to R. See, for all x comma y belongs to R, we have y comma x belongs to R. So therefore what I can conclude? R is symmetric. Now let's prove the third property. Now take x comma y belongs to R and y comma z belongs to R. So this implies what? X minus y is an integer and y minus z is an integer. Take the sum of these two. Take x minus y plus y minus z. This is also is an integer. Why it is an integer? Because sum of integers, sum of two integers is again an integer. Hence, x minus y plus y minus z is also integer. We can cancel minus y plus y. This implies x minus z is an integer. If x minus z is an integer, then it should be in the relation, that is x comma z must belongs to R. So therefore, for x comma y belongs to R, y comma z belongs to R, we have x comma z belongs to R. So therefore, what we can conclude? R is transitive. So therefore, we have R is a reflexive relation, R is symmetric relation and R is transitive also. So therefore, what we can conclude? R is an equivalence relation. So this is how we are going to verify the types of relation, that is whether R is reflexive or R is symmetric or R is transitive based on the given condition. If all the three conditions are satisfied, it is called as an equivalence relation. Otherwise, it is not an equivalence relation. So, I hope you understood the types of relation clearly. We'll meet you in the next session. Until then, keep watching, keep learning, keep exploring. Thank you.